This video is going to give you just, I guess, a few more detailed instructions for the horsepower lab. Um, our goal here is to figure out the horsepower of our mouth. We're going to be drinking some water through a straw out of a cup and doing some measurements and some calculations. The one thing you need to be very careful of when we did work calculations in MyLabs Plus, everything was in metric, and most of the problems ended up with final units of either newtons or joules. In this lab, everything is going to stay in US units. So you're going to see that all of our calculations are going to be in inches and pounds, and then towards the end, we're just going to do some conversions between inch pounds and then foot pounds. And then finally, we'll incorporate the time that it took us and do foot pounds per second. And then horsepower is actually a unit of foot pounds per second. So we can do a conversion between foot pounds per second and then horsepower. And you'll actually find out that in horsepower, the sucking power of your mouth is very, very, very small. So if you compare that to things that normally are measured in horsepower, like the power of a motor, you will see that you really do not have any power in your mouth at all. So I'm just going to go through some of these instructions really quickly, and these are some things that a lot of times I have to make some clarifications with my on-campus class. It's kind of important that you have a transparent cup. It doesn't necessarily have to be a disposable cup. You can always make the mark for your water and then just erase it or wipe it off later. You want to make sure you have a sufficient amount of water in there. You don't want to get too large of a glass, or you might make yourself sick because you do have to drink all of the water in the glass. But also you don't want to have just a tiny little bit at the bottom. Otherwise, it's not going to take you any time at all to drink the water. And the smaller the amount of time, the less accurate the time calculation or the time measurement is there. So you're going to start with a transparent cup, and you're going to put some water in it. I didn't have a disposable cup, so what I did is I found this little cup in my cupboard. It's actually glass. I don't have any water in mine just because I'm going to be manipulating it for you, and I didn't want it to spill on my desk here. So you're going to fill this partway with water. I'd probably put about 8 ounces or so in there, which is 1 US cup. You could do a little bit more as well, and that would be fine. So I just marked where I have my pretend amount of water in there. And we want to measure exactly how much water is in here vertically. Now, one mistake I've seen students make in the past is when they measure this, they follow the slant of the cup, and that's going to be a different height than if you were to measure it perfectly vertical. And we need to measure this perfectly vertical. So you make sure that your cup is on a table and that your ruler is also resting on a table, and get this perfectly vertical height. And that's the first thing that we are asked for in step number 2, is to measure the height of your water. In step number 3, you're going to time yourself drinking that water. And if you need to, you can get somebody to help you. I suggest using a timer on a cell phone or a stopwatch. That way we can get like to the nearest tenth of a second or even hundredths of a second. If you have a bendy straw, so here my straw has the little accordion thingies that allow it to bend. Do not bend your straw. Keep it perfectly straight. If you were to bend it, that will throw off our calculations, because later on we've got to take into account how far up the straw we have to carry the water. And if that were bent, we would have to then break it into 2 calculations and use some trigonometry, and we don't want to make this any harder than it needs to be. So we're going to drink the water out of the cup with a straw. Make sure the cup or the straw is in there perpendicular to the bottom of the glass, and do not bend the straw if it is a bendy straw. Keep it perfectly vertical all the way through. And then you're going to time how long it takes you to drink that water. And that's what we want there in the second blank. For step number 4, we've got quite a few measurements to take and then quite a few calculations to do. And this is going to serve two purposes. It's going to take our cup and it's going to create a model for it in terms of a volume of revolution like we did in section 3 and section 4. And then it's also going to calculate or at least set up the integral that we would use to calculate the volume of our water using the disk method that we learned in section 3. And this is again why I did not put water in this. If you look at this from the side, you will see that if we had a function to represent the slant of the side of this cup, we could then take that and revolve it around the x-axis and turn it into a volume of revolution. So what we need to do is we need to pretend that the x-axis is going right through the center of the bottom of the cup. And we need to take two measurements to figure out how to calculate this radius function. So the easiest way to do this is consider this edge of the cup to be perfectly flush with the y-axis, and that would give it an x coordinate of 0. And then we can mark how far up the y-axis it goes just by measuring the radius of the bottom of the cup. So use your ruler to just measure the radius. And again, if you want to, you can do that to the nearest 1/4 of an inch or 1/8 of an inch. It's up to you. And then we'll also measure the height of the cup. And again, that needs to be perfectly vertical. So set it on a table and set your ruler next to it also perfectly perpendicular to the table to see what the total height of your cup is. That's going to be our second x coordinate. And then we're going to take a radius measurement at the top of the cup. And that will be the y coordinate for our second point. So we're going to have 2 points to help us figure out this equation. Our first point is going to have an x coordinate of 0 because it's at the bottom. And we're going to measure the radius for our y coordinate. And then we're going to measure the height of the cup. That's going to be our x coordinate on our second point. And then the radius here at the top, that'll be the y coordinate for the second point. So that's what they want in part B, the 2 points that you're going to use for the radius. And we want these measurements in inches. Everything we're doing right now needs to be in inches. Now, once you know those 2 points, you can use what you've learned in algebra to figure out the equation of that line. So the y equals mx plus b formula, you can calculate the slope if you know 2 points on the line and go through that whole process to figure out the equation of the line. Now I'm going to jump back to part A. It says draw an accurate graph using inches for the scale of your cup as a volume of revolution. Now there is a link on our Moodle page for a piece of 4x4 graph paper. And 4x4 means that 4 squares equals an inch. And when you draw this graph, you need to draw it accurately. Don't just randomly assign one box to be 1 and the second box to be 2 and the third box to be 3. You need to use 4 boxes equals 1 inch. So 8 boxes will take you out 2 inches, and then 12 boxes will take you 3 inches. We want it to be an accurate depiction of exactly what our cup looks like. So once you have the equation of that line, you have those 2 points on your radius, we can draw a good accurate depiction of what this cup looks like as a volume of revolution. And we're specifically going to use the disk method. We're going to be revolving this about the x-axis. In part D, it says set up the integral. Now, I don't want you to calculate that integral. I just want you to write what the setup of that integral looks like for calculating the volume of water in your cup. Now, this is just going to be a simple disk method problem. You now have your function from part C that represents the line that we're revolving around the x-axis. The trick here, though, is we don't want to go the full height of the cup. We only want to know the volume of the water. So on your limits of integration, your upper limit of integration is just going to be how much water you had in your cup. Do not calculate this integral. We're using this integral to help us kind of as a preliminary step to work towards our work integral down in part G. Okay, so we just want to know what this this disk method integral is going to look like for volume. In part E, we want to know the distance that the water needs to be moved, which is the length of your straw. So just use your ruler to measure the length of your straw. This is the total distance that the water has to get moved up the straw, or moved up out of the cup. So for part D, it just wants to know how long our straw is. Again, do not extend this, do not bend this, just keep it perfectly straight. If you remember back in the section on work, we the algebra formula for work is force times distance. But if force is variable, like it is in this case, all of the pumping problems have variable force when you're acting against gravity, especially when you have a vessel like we have where the sides are not perfectly vertical. So we've got this radius function where our layers of water are circles, but they're different size circles. We're going to have to use an integral to calculate work. So when we integrate force, we can also get work. Force in US units, one of the common US units to measure a force is in pounds. So the way that we're going to get pounds into our volume integral is by including how much this water weighs. So just as an approximation, we're using that water weighs 62.5 pounds per cubic foot. That is a common value that is used, but unfortunately in this problem, because we're working on a small scale, ours is per cubic inch. So you're going to have to do some dimensional analysis to change that 62.5 pounds per cubic foot into pounds per cubic inch. So for part F, we just want to know what that decimal is if you were to change it to pounds per cubic inch. Including that value in our integral will introduce the pounds unit. So if you look back at your integral, what you'll have inside your integrand is your radius function squared. And radius is measured in inches. So the total units we have in our integrand are inches squared. By including the weight of the water, we now have pounds per cubic inch. So some of those inch units will cancel. So now we'll be down to pounds per inch. We need to include one more value that's measured in inches so that all we're left with in our integral is pounds. And that's where the length of this straw comes in. We need to also indicate somewhere the distance that the water needs to get moved up in the straw in inches as part of our integral. So when you put all three of those pieces together, so D is going to be your starting point, then you're also going to include the weight of the water and also the distance up the straw that the water needs to be moved. And that is going to be an expression that uses the height of the straw and also X. It's not all of the water needs to be moved the full height. The distance it needs to be moved changes as water is sucked out of the cup. So if you're confused by that, just look back at some of the problems you did, the pumping problems you did in section 6.7, and hopefully that will help. And that will create for us our integral for calculating work. You should be, if you identify all of the units for all of the values in your integral, you should be left with something that's just in pounds. All of the inches should cancel away, and you'll be integrating pounds over the height of your water. In G, we do not want to evaluate the integral. G just wants to know what that integral looks like. In H, you're actually going to do the integration and tell me what the value is. Now, you don't have to show out the work of calculating that integral by hand. Once you get that integral set up in G, you can go ahead and just type it in your calculator. The units here, be really careful. Our force is in pounds, and that force is being used to move the water a distance that's measured in inches. So right now this work is in inch pounds. So H is going to be in inch pounds. So we'll have work once we get to the bottom of step number 4 in inch pounds. And then the final couple steps here are just to convert our inch pounds into horsepower. So first we define power as foot pounds per second. Right now we have inch pounds, so you're going to have to first convert your inches into feet, again with dimensional analysis. And then this is the step where your time is going to come in. So up here, when you drank your water, you indicated how long it took you to do that. Since it's per second, you're going to also divide by the amount of time it took you. And this is going to give you your sucking power, the amount of power that your mouth has. Horsepower is just one specific measurement of power. 1 horsepower is 550 foot-pounds per second. So if you know how much power you have in foot-pounds per second, you can again use dimensional analysis and the horsepower conversion here to convert your power into horsepower, which we want to do in number 6. And you will find that your value here in number 6 is really, really small. It's going to most likely have some scientific notation with like a 10 to the -4, -5, or -6. It's really, really tiny. Page number 2 is just the rubric of how this is going to be graded. When you turn in this project, you have to turn in the first page with all of your blanks filled in, and then you also need to turn in your graph. And your graph should represent a to scale model of your cup as a volume of revolutions. Those are the 2 things you need to turn in. So you're going to be graded on the accuracy of your graph, the fact that you completed everything on the previous page, and then I'm going to check that everything is mathematically correct and that you followed all the directions. If you have any further questions, or if you are having trouble with these conversions, first I suggest you Google dimensional analysis if it's been a while since you've done any sort of conversions like this. But if you're still having trouble, just email me and let me know, and I'll be happy to help. And have fun. This is a pretty interesting project, not quite as time consuming as the last one, but it usually ends up being pretty fun.